Alright, so I'm going to solve a Putnam problem. In case anyone is taking them, I think it's a good idea to take them. Try it. Or just study for them. That's a good, fun thing to do. Okay. So I'll tell my stories and stuff after. This is a Putnam problem. This is from 2016. And it says B3. Okay. Some people say that I've heard that the B section is harder, or that you shouldn't try them or something. But I don't think that that's true. I think that actually some of them seemed actually easier. Okay. So for this one, and for a lot of Putnam problems, or just problems in general, like in geometry, for the proof, we're going to need, the main thing that we're going to need is similar triangles. I've seen more than one Putnam problem where they use similar triangles. So I'm just going to go over how do we notice or just be able to prove or state why two triangles are similar. Okay. So we'll say the triangle ABC is similar to triangle A prime, B prime, C prime. So that's similar. If the corresponding angles are the same. So I'll just say it this way: angle A is equal to angle A prime, angle B is equal to angle B prime, and angle C is equal to angle C prime. So the ways that we can conclude the two triangles are equal, well, if they have the same angles, if we can find the same angles. So this is just a review, so I'm not gonna. So if they have the same angles, then we know they're similar. That would be good. But even if they just have two of the same angles, two of the same corresponding angles, and the third one we could find, must be the difference 180 minus those other two angles, and the other one's 180 minus those two angles. So actually that would be enough to conclude that they're similar. The other one, for the other two, is, so let me just write this one out a little bit more. So if the ratio of AB to A prime, B prime is the same ratio of BC to B prime, C prime, and that's the same ratio of AC to A prime, C prime, then we can conclude that the two triangles are similar. Okay. So this is, the abbreviation is SSS. Okay. So let me just erase this for a second. So this is the other way, and then the other way we can tell if two triangles are similar is if, let's see, AB, the ratio of AB to A prime, B prime is equal to the ratio of BC to B prime, C prime. So this ratio of this side to this side is the same as the ratio of this side to this side, and this angle is the same, then we can also conclude similar triangles. And angle B equals angle B prime, then we can again conclude that they're similar triangles. And this is abbreviated SAS. So when I was first doing this problem, this one is the one that I know for sure. Like if I'm just thinking about similar triangles, I know this one for sure. So if I can find all the angles the same. So that's the way I did it the first time. But then just when I was like writing this up to present it, I saw that this, I think we can use side angle sided, is actually a simpler proof. So I'm just gonna mention how I did it this way, because you can still do it. It's just more like brute force method. And then this one, once you see it, it's nice. Okay. So that could be also, I guess, a tip if you do have time. You could, if you feel like you're onto something, then you can, when the act of writing it up can illuminate, and let you see some nicer ways to do it, which is what happened here. Okay, to me. Okay, so what's the problem? Okay, what's the problem? Oh my god, I didn't even say. What's the problem? Okay, so let me write the problem. So this is the main thing that we're going to need. Okay, what's the problem? Okay, this is Saturday, December 3rd, 2016. Okay, and if I remember correctly, you have 3 hours. You take the first part. I'll show you what it looks like. Okay, so you have 3 hours to do. They give you 6 problems, and then you have take a break, and then you have another 3 hours to solve 6 more problems. Okay, and I think it's always on a Saturday, 1st December. Okay, so this one was, okay, suppose that S is a finite set of points in the plane. Such that the area of triangle ABC is at most 1 whenever A, B, and C are points in S. So show that there exists a triangle of area 4 that contains all of S. That, together with its interior, covers the set S. Okay, so we're in the Cartesian plane. So the first step, I guess, okay, I'm going to give you loose advice, and I'll tell you my score that I got at the end. But I think that if you find a problem that you like, to try and understand it, just understand the sentences, maybe even write it down yourself, and see if you can just understand what is it even trying to ask you to do. Okay, so in this case we have start drawing pictures, especially for one like this that's all about the plane. So somehow I have a set S that's on the plane, and there's finitely many points in S. And this is saying that. So for example, here I'm going to try and draw like what I think is the biggest triangle I can out of here. Okay. So let's just say that's A, B, C. So I try to find the biggest triangle I can, and I know that the maximum area of that is 1. So I want to somehow find a triangle so that can cover all of S and its area 4. So let me tell you the parts of this. This is after solving and then going back and writing it up. So the 3 parts of this are, so this is part of the first part, is visualizing it, seeing what the problem's actually asking, and then the big trick. So the big trick, how does this come up? Well, that's some, you have to be inspired or something, or maybe I'll talk about how you could come up with that. I don't know. Well, maybe because you've seen it before. Maybe you saw that here and you saw this trick. So, okay. So in this, it's like a visualizing trick. So that's the first part, is just kind of what's our strategy, or what do we think is the solution? Okay, and then we're going to prove that it's true. The second part is we're going to use similar triangles to show that whatever we did in part 1, that we get an area close to 4, and then we're going to use then we're going to show that this bigger triangle contains all of S. So first, what is this bigger triangle that's going to contain all of S? Okay, so let's start playing around with this picture. Okay, so let's say we're just playing around. We don't know. All we know is we have some dots. I'm trying to motivate how you would come up with the inspiration to do what I do next, but I can't really. So I'm just gonna let's pretend that this is how you came up with it, I guess. So you know that there's some dots and you see a triangle, and maybe you're just messing around. You're like, okay, well, how do I get it? I mean, I don't know. Somehow you're doodling and you come up with this shape. Okay, it's like, okay, something's happening here. Okay, I've got a triangle. Biggest triangle that can contain S. Okay. Somehow, this is a bigger triangle that contains S, and I like it because it's like, it looks to be 4 times as big as the original one. Okay, this is the big trick. How we get there, I don't know. So here's the big trick. So let's just draw a sample what S might look like. I'm going to draw the biggest triangle I can. Okay. Okay, see, I'm just going to go with what I have here. This seems to be biggest triangle I can. I'm moving that just because. And like this. Okay. So by the hypothesis, I know that this has area 1, but okay, I'm not really there yet. So I'm going to try and draw this figure. So what's really happening is my idea is I have a triangle, and I'm taking the midpoints of the bigger triangle, and that's the triangle ABC that maximizes the area. So it's actually easier to draw the big triangle first. Okay, but so here's what we're gonna. So maybe we've seen this before. We came up with it on the spot, and we're gonna just try and prove that this is the triangle we're looking for. So my hypothesis, or let's say my conjecture, is that if this is the triangle, if ABC, so given that ABC maximizes area, okay, meaning like A, B, and C are the points that maximize the area of a triangle, then form a triangle A prime, B prime, C prime, like this. Where B, let's start with A is the midpoint of B prime to C prime. B is the midpoint of A prime, C prime. Okay. And C is the midpoint of A prime, B prime. Okay, just like this. Okay. So we've got the picture plus starting to articulate what we did articulate what the bigger triangle is, and now we're going to prove. And so our conjecture is that triangle A, B, and C is what we're looking for. A prime, B prime, C prime. Triangle A prime, B prime, C prime works. So first we have to show two things. We have to show that it has area 4. What we're going to show actually is that it has area at most 4, and then you can just scale it up a little bit to have an area exactly 4. And then we have to show that it contains S, or that it covers S. Okay, I'll leave this. I'll leave this picture up here. Yeah, it's a lot easier to draw from the bigger one first, but okay. So in this case, it did seem to work, right? It seemed to cover S, as we hoped. Okay. So this part is we're going to show that the area of triangle A prime, B prime, C prime is at most 4. And the idea is that show all the triangles in here are similar triangles, and therefore they're actually equal because they share sides. So if this area is at most 1, then the area of the bigger triangle is at most 4. Show the let's see, I'm just going to say it this way, all 4 triangles. I'm just kind of writing up the idea to myself before I write it up. In the bigger triangle, A prime, B prime, C prime are similar and therefore equal. Okay. So let me draw another version of my picture. B prime, C prime, A prime. So I'm picking up the midpoints. Okay. So I'm going to use side angle side. to show that this triangle here is similar to the bigger one here. So I know that this is the midpoint. So the ratio of this side, AC, so AC, A prime C is to A prime B prime. Since C is the midpoint, this is A prime to B prime is twice A prime to C. And similarly, this, since B is the midpoint, A prime to C prime is twice A prime to B. Okay. And they share the same angle, so angle A prime equals angle A prime. So therefore, a triangle CA prime B is similar, so this triangle is similar to triangle B prime A prime C prime. Okay, we can do the same thing here. I can show that this triangle is similar to the bigger triangle here. So also by side angle side. So C prime to B, the length of that segment, to C prime A prime is the same ratio as C prime to A over C prime to B prime. And they share the same angle. Angle C prime is equal to angle C prime. So this implies that triangle B prime, C prime, A prime is similar to triangle A, C prime, B. And again, with from side angle side, we can get that this triangle is similar to the bigger one. So B prime, this line segment, is half of the line segment B prime to C prime. And that's the same ratio as this. A prime C is to A prime B prime. And they share the same angle. So this, we can draw the conclusion in that triangle A B prime C is similar to triangle C prime B prime A prime. So then I'm going to use this fact to show that this triangle in here, ABC, is similar to A prime B prime C prime. So far we've got triangle A, B prime, C is similar to triangle C prime, B prime, A prime. And we've got triangle A, C prime, B is similar to triangle B prime, C prime, A prime. Which ones did I do? Those two? Okay. And then triangle C, A prime, B is similar to triangle B prime, A prime, C prime. Okay, so from here I'm going to conclude that, okay, this AB, the ratio of AB to A prime, B prime must be the same ratio as AC to A prime, C prime, using all these similar triangles. They're all similar to the bigger one, so they're all similar to each other, but I'm actually not using this. They're all similar to each other yet. I'm just using the similarity of each of these to the bigger one. Okay, what else? And let's see, where am I? And AC, AB, and BC. Okay. So then this gives me side, side, side. So this implies that triangle ABC is similar to triangle A prime, B prime, C prime. Okay. So therefore, all of these triangles are similar to each other. I'm just going to write that these are all similar to each other. Okay. Okay, we're going to write this. We want to, write this all up clearly at the end. Okay, so these are all similar to each other, but they share. So all four triangles are similar. And they share sides. So they must be actually equal triangles. Okay. So I'm going to finish this thought. And I think I will show how do you, like at the end, just writing it all up, writing up the whole thing. Okay, so these are similar to each other. They must be equal to each other. Thus, if the area of each is at most 1, then the area of the bigger triangle is at most 4. So and then I would just say it like this, and I don't know if this would be enough actually, but I would say it like this. So if the area of triangle A prime, B prime, C prime is less than 4, find a bigger triangle that contains A prime, B prime, C prime by scaling. So I'm just going to take a slightly bigger triangle. That's how I would say it, just a sentence. It is exactly. So now we have this triangle that has area 4. All we have to do is make sure that it covers S. That's the next part. But all of S will be contained in A prime, B prime, C prime. Okay, so the scaling is just to get exactly area 4, because that's what the question said. Exactly area 4. Okay. So I'm going to draw this again in black here. So A prime, B prime, C prime. C, P, A. we're going to show that triangle A prime, B prime, C prime covers S. Okay, like it did here when we were just playing around. So let P be an S. Okay, so I'm going to draw P. I'm going to draw it here. Okay. It's in S. Okay, we'd like for it to be inside the triangle, but along the way I'm going to say, well, what if it's not? What if it's out here? So right now just think it's generally there. I happen to put it inside. But we'll play with, well, what happens if it's outside? Okay, we're going to see that in a second. But P isn't, just let P be a point in S. Hopefully it's in there. If it's in there, then we're done. But if not, okay. But so I'm going to just draw it like that. But I will move it. Okay. Okay, so we know by the hypothesis, really our only hypothesis, besides the fact that S is finite, is that the max area of a triangle is 1. So that gives us the triangle PBC, whatever that is, has to have area. So the area of this has to be less than the area of triangle ABC. Okay, so that's the one with the max. Okay, so I have 3 claims. So my claim, I'm going to call this H1. Okay. So P. What I want to say is, before I write down my 3 claims, what I want to say is that P is in the half plane. So we're going to divide the plane into 2 pieces, with each of these segments. Okay, so I'm going to take the plane. Divide the plane in 2 by this, and I'm going to show that P must be on the side of this half plane bounded by this line segment that contains A and B. Because if it doesn't, if it's outside over here, then I have a bigger triangle with points from S that's bigger than the area of the max, of the triangle that has the max area. Okay. So I say, so P must lie, so H1, in the half plane bounded by B prime, C prime, containing B and C. So if we can argue this, then we can argue all 3 of my claims, and I'm going to write them each down. Okay, so if not, what's going to happen if not? So let's say that didn't happen. Okay, so my claim is that P must lie in the half plane bounded by B prime, C prime, on the side containing B and C. So on this side of the plane. So I think of the whole plane cut in 2 like this. Okay, and P must be over here. Okay, but what if it's not? What if it's over here? Okay. So suppose it's over here. Okay, so if not, then I can form a bigger triangle . PBC, which has a bigger area. Or you could just say If not, then the area of triangle PBC has greater area than triangle ABC. Okay, when we write it up, I'll write it like that. Okay, and if you want to see why, and I mean, of course, you can write up as many details as you want. If you find a detail that you can prove, that's good, I think. But okay. But these have the same base, but they have different. I mean, the height of this triangle has to be bigger because it's further out than A. Okay. But I also think that at least you can go too far into the details and you want to get the main. Okay, so this is the contradiction. So the area triangle PBC would be greater than or equal to. Okay. Okay, so my second claim, so this is H1, is that P is on this side of the line segment B prime, so we know it's over here somewhere. Okay. So my claim H2 is that P must lie on the half plane bounded by A prime, B prime, this one, containing A and B. And it's the same proof. If not, okay, so we've already got it over here. It's somewhere over here. But let's say it's outside, it's over here. Okay, again, we form a bigger triangle that has a greater area than a triangle ABC. So that's a contradiction. Okay, and then H3 as P must lie on the half plane bounded by A prime C prime containing A and C. Okay, so we've got it over here, and now we've got it in here. So the intersection of these three planes is it's precisely the region bounded by the triangle A prime, B prime, C prime. Okay. Then P is in H1 intersect H2 intersect H3. This is precisely in the region bounded by triangle A prime, B prime, C prime. Okay. So that's we got everything worked out as far as the idea goes. So I'm just going to go through. That's the proof. Basically, show that that it covers S and that the area is at most 4, and then we can scale it up to it so it's exactly 4. So I think it'd be good and helpful for me to just write up all these ideas as you might write up the solution to the Putnam. Okay. So now, let's just do that. problem, and this is the solution. Okay, sorry. Go through my notes that I was writing. So the first part is, okay, find A, B, and C. To maximize the area of triangle A, B, and C. Okay, and then I'm going to draw the picture here, but really I'm going to have to write everything out. So I'm just to remind myself. So this is A, this is A, B, C. This is B prime, A prime, B prime. Just to remind myself. Okay, and so I really want to write what A prime, B prime, and C prime are. So let A prime, B prime, C prime be such that A is the midpoint of B prime, C prime. B is the midpoint of A prime, C prime. And C is the midpoint of A prime, B prime. Okay, and then let's state our claims. So we have two claims. One is that the first one is that the area of triangle A prime, B prime, C prime is at most 4. I'm abbreviating a little bit here, but yeah, it's always nice to write in full sentences. Okay. So the way I did that, so I'm just going to write in symbols the way I did it. So proof of the claim. Okay. I'm going to write the abbreviated version of what we proved basically, but I think it would be great to write down the details that we showed. Why does side angle side like why does side angle side, the little details to show that because of side angle side, this triangle is similar to this triangle. So I'm just going to write what we concluded, but we can show by side angle side. Okay, so by side angle side, we get that triangle CB prime A is similar to triangle A prime, B prime, C prime. We get the triangle, I'm just going to say and each time, and triangle, this little one is similar to this bigger one, and triangle B, A prime, C is similar to triangle C prime, A prime, B prime. And triangle okay, which ones did I do? Let's see. I did C, B prime, A. I did B. Okay, so this one. So triangle B, C prime, A is similar to triangle A prime, C prime, prime. Okay. Okay, so this gives us then maybe I should just I'll just try and fit all of claim 1 in here. You know, fill in more detail, and then I'll try to do all of claim 2. I'll erase this and do all of claim 2. Okay, so then CB, the length of this CB is the proportion of this to C prime B prime is the same proportion as AC to A prime C prime, and AB, the length of this line segment, is the proportion of these two line segments is the same as this one and this one. So then this thus by side, 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 triangle ABC is similar to the bigger triangle A prime, B prime, C prime. Okay. So now what we've concluded is thus triangles A prime, B, C, B, C prime, A, C, A, B prime, and the one in the middle, triangle ABC, are all similar to each other. Okay. But since they share sides, they must be equal. So they're all the same area. So, so the area of triangle A prime, B prime, C prime must be at most 4, because they have 4 triangles all with area at most 1. So the area of A prime, B prime, C prime must be at most 4. By homothety, okay, okay, I'm just gonna say this: if necessary, scale up I'm just gonna say scale triangle A prime, B prime, C prime to be exactly 4. Okay, it's not good to make something up if you don't know it, but if you're not sure of the word or something, you're not sure if like what's the exact mathematical thing that's going to allow me to do this, but you feel like it seems valid. I think it might be okay to make a solid confident statement about it. Okay. Okay, I've never graded these or anything. Okay, so now we've got the area. We can find a triangle of area exactly 4. Okay. But all of S will be contained in this triangle A prime, B prime, C prime anyway, so that's what we're going to show in the next step, and then we got to the conclusion. Claim 2 is that triangle A prime, B prime, C prime covers S. Along with its interior covers S. So I just want to write this up the way that exactly the way we did it. So let P be an S. The area of triangle PBC is less than. I was just thinking, should we say less than or equal to? But if it was equal to, then we just use those points instead. Okay. Okay. So the area of triangle PBC is less than the area of triangle. This is given. It's given. I mean, this is because of the hypothesis. Okay. So P must lie in the half plane bounded by B prime C prime containing B and C. Okay. And we could show more. We could show more details here, but I'm just going to say, since if not, the area of triangle PBC could be greater than or equal to triangle ABC. And we showed that because they'd have the same base. And but the heights might be. So I didn't really show that case. Like if like I could pick a P right here that wasn't off kilter, like here. Okay. And so they have the same base. Oh, okay. Yeah, I mean that's the easiest case. If it was a little bit off kilter though, they might have the same area. Okay. I think I'm going too much into details. Okay. Okay. And P must lie in the half plane bounded by A prime C prime containing A and C, and P must lie in the half plane bounded by A prime B prime containing A and B. Okay, let's make that into a nice full sentence. Okay. And so therefore we'll say the intersection of these planes is the region contained is the region bounded by triangle A prime, B prime, C prime. Okay. So P must be inside of this triangle. Okay, it could be here. It could be I guess it's on the Maybe think about all the different cases. Okay. Okay, so therefore, triangle A prime, B prime, C prime covers S. Okay. I'm thinking about what happens if P is on the line. Okay. And they would have the same area. Okay, I think that would be the case. Okay, but I'm sorry. That's just something that's like a little bit fuzzy in my mind. So I would I would try and go through the details. Okay, I think that's pretty much it. So I hope you enjoyed that. I think it's good to go through. I mean, just even when I did this for math club here at my school here, and we went through a few problems, and just to see like if you just see some of the problems, maybe it's something similar will come up on your exam. But when I was an undergrad, also just the club where you study for the Putnam itself, it can be really fun. So even if you don't take the test or if you don't do well, nobody does well. It's okay, nobody does well. But okay, and so but there are all the old exams online, and they have solutions, but they're like little hints basically. Like for this one, it's like this little hint. But I think it's really helpful to just try and go through a solution and see if you can fill in all the details. Just for fun. Okay. Well, thanks for listening, and hope it helps in some way.